Hi, welcome back to College Algebra. This is week 12. We'll talk about radicals and rationalization and how to solve some radical equations as well as completing the square. We'll cover 6.6, 6.7, and 7.1 from the textbook. And then as always, please look over the measurable outcomes, skills that you need to know for this week. Okay, division of radicals and rationalization. This might seem a little confusing, but I think when we do some example, it'll make more sense. The point here is that we want to simplify a radical, and there's three rules that we need to follow for a radical to be considered simplified. And the first one is that the radicand has no factor raised to a power that is greater than or equal to the index. Again, that's confusing, so I'll show you that in a second. The radicand does not contain a fraction, and no radicals are in the denominator of a fraction. And so let's first, before we do anything, let's talk about the division property of radicals, and that is, if I take the nth root of a over b, that's the same thing as take the nth root of a divided by the nth root of b. In other words, we can take the nth root of each of the individual numerator and denominator, do it separately, and then divide. Okay, so for example, suppose I have these two problems, and I want to simplify these radicals using the division property. And so for the first one, notice that the radicand contains an irreducible fraction. In other words, this fraction right here cannot be reduced. And so we use the division property by taking the radical of each of the individual numerator and denominator. So the square root of a to the 6 is a cubed. The square root of b to the 4 is b squared. And so this is using the division property. And then this is very similar. Again, I can't simplify this. The y and x, they don't cancel. 81, you can't do anything with this. You can't simplify this. And so we apply the division property. So I want to do the cube root of the top and the cube root of the bottom, and then divide them afterwards. And the way to do this is that we saw from last time that we can factor out each of these terms. So 81 is 3 to the 4th, y to the 5th. And so that means that because we're taking the cube root, we take out there's a component here that is a cube that we can take out of the cube root of 3 cubed, for example, is just 3. So 3 cubed in here can be moved out to become a 3, because again the cube root of 3 cubed is 3. So if I take out 3 cubed, then what's left is a 3. So there's a 3 remaining inside. Y to the 5th. Well, again, there's a perfect cube inside of this as well, and that perfect cube is y cubed. So the y cube in here can come out. When you take the cube root of the y cube, you get a y, which is outside now. And so if I take a y cube, I have y squared left. And so notice that the 3 and the y squared is what's left after I take out the perfect cubes by cube rooting. And this is similar. The cube root of x cubed will cancel, and I get just x. Okay, and then now if I have the opposite problem, which is that if I want to cube root of the fourth root of 8p7 and then divide by the fourth root of p cubed. So this is the opposite problem, where maybe I want to do the reverse. In other words, instead of doing them separately, which I can't do in this case, I'm going to combine them by taking the cube root of the quotient instead. And so by looking at the quotient, we notice that we can cancel. So unlike the previous example where we can't cancel the fraction, in this case, because we can cancel the fraction, we should use the division rule in reverse. And so now notice that p7 divided by p cubed is p to the 4th, and now we can simplify this further. The fourth root of p to the 4 is just p, and then the 8 is just going to stay inside of the radical. And then the last condition of that we need to remember from simplifying a radical is that sometimes we don't want a radical at the denominator of a fraction. And so the process of removing this radical from the denominator is called rationalizing the denominator. And so there's really a couple cases. One case is where you have a radical at the bottom, which is a one-term radical. Another case is where you have a radical but is kind of a binomial, where you have two terms that have been added together. So one term versus two term. And so we have to cover both of these. So one term versus two terms. And so first we want to be able to know how to multiply a radical by another radical that can cancel the radical. and this is very important. So for example, square root of a times what is equal to a. So we want to find a way to get rid of the radical. So notice that if I put an a here, then using the property of radical, a times a is a square. And so instead of taking the radical of a times the radical of a, I can take the radical of a times a. And notice the radical of square root of a square is just a. And so by multiplying the radical of a by radical of a, I can cancel out the square root and get a. And that's what we want to do with when we have a radical at the denominator. Here's another example. If I take the cube root of y, what do I have to multiply by? What cube root do I have to multiply by so that the cube goes away? Well, if I have a y here and I need a y square and a y give you y cube, and that is a perfect cube. So the cube root of y cube is y. And then finally, here's a fourth root. What do I have to multiply? What fourth root do I multiply by so that the fourth root will go away? So I have a 2 here, so I need 3 more 2s so I can get a perfect power of 4. And so for example, here's a 2, so I need a 2. I need a 2 cube, so that and the 2 and the 2 cube becomes 2 to the 4. I have a z cube, so I need another z so that the z cube and the z becomes z to the 4. And now both of these power to the power of 4, so the fourth root of that is just simply 2z. So let's see how this works. So if I want to simplify this expression, notice that I have a radical at the denominator, and so I want to get rid of this radical. And so I need to figure out what to multiply by at the denominator so that the radical goes away. And I need to multiply both the bottom and the top by the same expression, so I don't change my expression. Just like in the last example, to get rid of the cube root of a, I need the cube root of a square, because then a and the a square becomes a cube, which will cancel with the cube root. And so I need to multiply this expression by the denominator and the numerator, because I'm essentially multiplying this expression by 1. This divided by this will cancel, so I'm not changing my original problem. So now the reason why this is good is because now I can combine the denominator into a cube root of a cube. Right? A squared times a is a cube, and that will cancel, and I get a. And then the top, there's not much I can do. We just leave it like that. But the point here is that the denominator now no longer has a radical, and so this is considered simplify. Okay, same thing for this one. Again, I need to get rid of this cube root, so I need to multiply by another cube root, but I need to make it so that these terms will cancel with the cube root. And so 25 is 5 square, so I need another 5 so that I will get a perfect cube. And then I have an s, so I need an s square so that I get a perfect cube. And I multiply the top and bottom by the same expression. And then notice now that the denominator is simply combining these radical, and now we have 5 cube s cube, so this is a perfect cube, so the cube root of that will cancel and I get 5s, and then this is now simplify. And then maybe we can simplify by reducing to the lowest terms. The 15 and the 5 will cancel, for example, and I get a 3. Okay, what if I have 2 terms? Well, remember from one of the previous lecture that a plus b times a minus b, the cross term cancel. A times a is a square, a times minus b is minus ab plus ab. Those cross terms cancel, and then you have b times minus b is minus b square. And so we're going to use this trick to rationalize our expression that has a radical at the denominator. So as an example, 2 plus root 6 times 2 minus root 6. Notice these are also called conjugate when the terms are the same, except for this is a minus and this is a plus. And when you have this case, by using this formula, we notice that the radical goes away. The 2 times minus root 6 and the 2 times positive root 6 will cancel, and my radical is gone. And so what I have left is that it's just a squared minus b squared. So a squared is 2 times 2, which is 4, and minus b squared is just minus 6, and so you have negative 2. So if you multiply a term that has a radical like this with its conjugate, with the minus, then the nice thing is that the radical goes away. So this will help us reduce our expression by rationalizing the denominator. So for example, I don't want this radical here, so this is a 2-term problem. So I need to multiply this by the conjugate, top and bottom. So notice 2 plus root 6 times 2 minus root 6. These are conjugate. So now again, because of that property we saw earlier, if I FOIL this out, if I multiply everything out, the radical goes away. And so, for example, 2 times 2, that's 2 square, and then root 6 times negative root 6 will give you a minus 6 here. So 4 minus 6 is at the bottom. Notice the radical is gone. And then the top, I'll leave it like we can't do very much. And then I can simplify the bottom, for example, to become negative 2 here. I can cancel these negative 2, and then I have the final term. Notice now, the point of doing this is that the radical, which is at the bottom initially, is gone after I multiply by the conjugate. Notice here, this denominator has no radical. And that's what allows us to simplify, by getting rid of this radical. So again, if you have 2 term, then you want to multiply by the conjugate to get rid of that radical. So here's another example. So again, this is a 2-term expression that has a radical, so I need to multiply by the conjugate. So root x minus 7, so root x plus 7, that's the conjugate. And then as before, if I multiply this out, the bottom will go away because root x times root x is just x, and then minus 7 times plus 7 is negative 49. Again, the cross term cancels, so we don't have to worry about those. And then the top, you have to do some foiling on top, which is first, outer, inner, and then last. But we do that out. It's just a lot of tedious calculation. But when I combine like terms, I notice that these two can be combined. For example, so 4 root x plus 7 root x is 11 root x, and then the other terms are not the same, so we can't combine these. And then that's our simplified version. Okay, solving radical equations. So a radical equation is an equation that has a radical in it. So for example, the cube root of x is 5. That's an example of radical equation. So we're going to use this property that whenever you have an nth root and a ratio to the nth power, the nth root and the nth power essentially cancel. And so we can do that by doing this, we can get rid of the radical. So for example, here's a radical equation. I want to solve for x, so I want to get rid of this radical by cubing both sides of the equation. The cube root of x cubed will cancel so that you have x left, and then 5 cubed is 125. Now the problem with this is that sometimes you might have a solution that introduced that are not solution. So for example, the root of x is negative 7. If I square both sides to get rid of the radical, I get that x, this square will cancel, x is 49. But 49 is actually not a solution to the original equation. If I plug 49 into here, square root of 49 is positive 7. So that means that 49 is an extraneous solution. It's a solution to this new equation, but it's not a solution to the original equation. So it's called an extraneous solution. Okay, how do I solve radical equation? The idea is that we want to isolate the radical, and then we want to raise it to that same index to get rid of it. Raise both sides to the same power as the index, and then solve the resulting equation. Now, after I do this step and I have a radical, I have to repeat this again. So let's see some examples. So I want to isolate the radical by subtracting 5 on both sides. So 9 minus 5 is 4, and now I can get rid of the radical by squaring both sides. I get 16. Again, we want to make sure that 16 is an answer by checking it against the original, because it's sometimes possible we might get a solution that is extraneous, but you can check that plug in 16 will give you that this will check out. So 16 is a solution. So here's another one. Again, I always want to isolate the radical, so I can move the negative 2 over to the right to get positive 4. And now I can get rid of the cube root by cubing both sides. So if I cube both sides, I get w minus 1 because the cube and the cube root will cancel. 4 cubed is 64. Bring the 1 over, I get 65. So w is 65. Again, I can check it to make sure that it's a solution. Okay, here's another one. Again, I always want to isolate the radical, so I first move the y over to the other side, subtract y, both sides, and divide by 2. I can divide by 2, or I can actually just square both sides right now. So again, if I square both sides, the square root here will go away. So if I square both sides, this side, notice when I square, I have to be careful because I have to use FOIL. So 3 squares 9, 3 times negative y times 2 is negative 6y, and then minus y squared is y squared. And then when I square this side, 2 squared is 4, the square root square will cancel, and now I can multiply and distribute. 4 times 4y is 16y, 4 times negative 3 is negative 12, and then try to put everything on one side. Whenever we get to the end, we always try to solve our equation by solving for zeros. And so let's move everything on the right side so that the left side is 0. Again, we always want to typically solve, when we solve these polynomials, we want the one side to be 0 so that we can factor and use the property we saw in the last lecture where we can set each of the individual factor to be 0. So for example, if I multiply everything on one side, put everything on one side, I get this. Let's try to factor this. This actually is factorable into, again, we can use a couple different methods, but it's y minus 21, y minus 1. You can check that this is the same thing as this. And then for this product to be 0, either this is 0, where y is 21, or when this is 0, where y is 1. So if I plug in 1 or 21, I get my two solutions. Now we have to be careful that these are not extraneous solutions, so we have to plug these back into the divisional, make sure that it checks out. For example, when you plug in 41, which is the one we got, we actually do get that we get an equation that's not true. So this is false, therefore 21 is not a solution, it's an extraneous solution. But when I plug in 1 though, it does checks out, so 1 is the only solution. So again, it's important to see that sometimes we might get a solution that is extraneous. Okay, I want to solve this. This one is one of the harder one, where you have a radical and a radical, and you have two radical, and so you want to solve for m. So one way to do this is to kind of separate the two radicals. So put the radical on opposite sides so that we can get rid of it by squaring. So let's move one radical into the other side. So now we square both sides. So this part left side is easy. If I square this side, the square root and the square will cancel. I get 3m plus 1. So that's easy. But this side though, however, unfortunately, when I square it, I still have a radical. Notice I still have a radical. So for example, square root of m plus 4 square is m plus 4. We have the cross term here twice. So 1 times root of m plus 4 times 2. And then 1 square is 1. So now we notice we still have a radical. And so we repeat this again by moving everything on the left side except for the radical. We try to isolate the radical. So if I move everything here to the left side, then I get that 2m minus 4 is 2 times root of m plus 4. Notice after I simplify, I move this over to the other side. And then now I can square both sides again to get rid of this radical. So notice we have to do this twice. So before I do that, let's divide by 2, and then I square both sides to get that. The right side is simple; it's just m plus 4. The left side is just some foiling. We get this, and then we move again. We always move everything on one side to solve for 0. Set everything equal to 0. So we get this. We can factor now into m minus 5. So m is either 0 or 5. Notice this one is one of the harder ones for sure. Right? We saw that we have to isolate the we have to separate the radical, square it once to get rid of one radical, and then simplify by moving everything on the other side so that the radical is isolated once again. Square again to get rid of the second radical. So it's a little bit more involved here. We can check that 0 when you plug back in is not a solution, but 5 when you plug in is a solution. So make sure that you always check your answer. Okay, square root property and completing the square. Okay, so we saw from one of the previous lecture that to solve a quadratic equation, we can factor and apply the zero product rule, which says that if I factor this into, for example, we want to solve any equation, I always want to solve for 0. So bring everything on one side by subtracting, and then factor this out. So if this product is 0, either this is 0 or that is 0. This is 0 when x is 9. This is 0 when x is negative 9. So these are two solutions. So we saw this method last time. Now in this section we'll learn another method that helps us solve an expression that cannot be factored. So notice this is easy because I can factor, but what if something is not factorable? So first of all, we want to use the square root property for some of these problems, and this says that if x squared is 7, and x squared is k, and k is assumed to be a real number that is non-negative, then x is either the square root of k or negative the square root of k. In other words, the solution to this equation is plus or minus root of k. So for example, how do I solve this? Well, I want to isolate the square, divide by 4 by both sides, and then take the square root. if I take the square root, then I get plus or minus square root of 9 over 4. But square root of 9 over 4 is actually, I can square root of 9, which is 3, square root of 4, which is 2. So I'm using that division property. And so P is plus or minus 3 over 2. These are two solutions. So again, whenever I have something being square, I can square root both sides, and I have a plus or minus as the two solutions. Okay, same thing here. I square root both sides to get a plus or minus root of 20. And then I can now simplify this actually by using one of the properties I saw earlier. I'm taking a square root, so I'm looking for some perfect squares in here. And so I do have a 4 is a perfect square, and a 5 is not. So the 4, which is a perfect square, can come out. Square root of 4 is 2. The 5 can have to stay inside because we can't do it. We can't simplify that. And then finally, I can move the 3 over. So it's negative 3 plus or minus 2 root 5. So that's the two solution. Negative 3 plus 2 root 5. Negative 3 minus 2 root 5 are the two solutions. So again, we're using the square root property. Okay, finally, if I have an equation like this where you have something being square, and I want to solve for w, I can square root both sides and then subtract 3 as we saw earlier. So this next method is called Completeness Square. Is where we hope to get to, if you have a perfect square trinomial that can be factored into something being square, then that's kind of the ideal case, because if I can do if I can factor this into this, I can take the square root to solve for w or for any variable. And so the goal here is that if I can take this expression and create a perfect square like this, that will help me solve my equation. But that cannot always happen, because we don't always have that these are factor nicely like this. So we have to make it so that it factor nicely like this. And so this process is called completing the square. And so for example, we notice that when you have a perfect square, this term right here, the 10 is actually, and this term is actually related, in the sense that if I take this 10 and I divide by 2, I get a 5, and I square that, I get 25. So that this term can be be used to produce this term. Again, take the middle term, divide by 2, square the result, and it'll give you this one. And then if this is the case, then this is a perfect square. And so that's why we need to kind of reverse this by creating a term that will make this into a perfect square. And so that's completing the square. So let's see some example. So again, the question here is that what is the constant here that I need so that this is a perfect square. And so again, the trick is that we need to take the middle term, 12, divide by 2, which is 6, square that, which is 36. So that 36 is the term that I need so that this becomes a perfect square. Notice if this is 36, then this whole term can be factored into x plus 6 square. And notice this 6 is essentially the square root of 36. And then for this term, it's the same thing. Take the middle term, negative 26, divide by 2, which is negative 13, square that, 169. So 169 is the term that I need so that this whole thing becomes a perfect square. And then this term is x minus 13. Again, notice this 13 is actually from the middle term divided by 2. And so the point here is that we need to find the constant that makes this into a perfect square. And so that will be something that we need to do to complete the square. Okay, so this is kind of you can read all this later, but let's just actually explain the process, and then you can go back and read this later in the slides notes. So again, I want to solve this equation by completing the square and then applying the square root property. So notice, ideally, I want this to be factored into a perfect square, but that isn't always. It's not always going to happen that this is a perfect square. So I need to use completing the square to make it into a perfect square. In fact, right now, this is not a perfect square. I cannot factor this into that form nicely, and so I need to complete the square. So what I do this is that I'm going to take the 13 and I move it to the other side, so negative 13, and then I'm going to complete the square to the left side. So again, the completing square process says that I need to produce a term so that this becomes a perfect square. So again, the trick is that to take the middle to the b term here and divide by 2. So negative 6 divided by 2 is negative 3. Negative 3 square is 9. So if I have a 9 here, then this will become a perfect square. In fact, this is actually this right here, x minus 3 square. And so I need to introduce this 9 so that this becomes a perfect square. But I cannot change my equation. So if I introduce a 9 on the left, I must also introduce the 9 on the right to balance my equation so that I'm not changing my equation. And then the left side, as we see, is now a perfect square. Notice is that negative 6 divided by 2 is negative 3. And that's always going to be like that. And then, so now this is square. Now I can square root both sides. And notice that I cannot square root negative 4 because the square root of negative 4 is undefined. So this equation does not have any solutions, any real solutions. It does have imaginary solutions that involve the I, but that's not part of this course, and so we won't cover that. Yeah, so but the point here is that we have something that is not a perfect square, but we make it into a perfect square so that we can use the square root property to solve for x. So let's do another example. So once again, right, I want to complete the square to this term. Notice that if this term is not a 1, I need to divide by it. So notice in the last example, if the quadratic term is a 1, this is very easy. But if it's not a 1, then I need to divide by this term to make it into a 1. So divide everything by 2 will give you this. Okay, now take the middle term, divide by 2, square the result. So 5 divided by 2, square the result is 25 over 4. Right? 5 divided by 2 square is 5 over 2 square, which is 25 over 4. This term is what I need to make this into a perfect square, so I add it to both sides of this equation. Now the left side, by virtue of adding this, is now a perfect square. And that perfect square is always going to be, well, m squared means that this has to be m, and then it's always this term divided by 2. 5 divided by 2 is 5 over 2. That is being square. So again, you can check that this is the same thing. And then the right side, you have to do some combining here, but I can come up with a common denominator being a 4. So multiply this by 2 and by 2 to get 6 over 4. I can combine these terms. And then now I have, because this is a perfect square, we can use the square root property by taking the square root of both sides. This will get plus or minus square root of 31 over 4. I can move this term over, become a negative 5 over 2, plus or minus root of 31 over 2. So now I have found m to be this complicated radical expression. And notice, right, this problem is hard because I can't factor this nicely, and so that's why we need to use this process. Okay, the good news is that this process is actually kind of complicated, and notice here it actually takes a lot of work. And so in the next lecture, we're going to talk about another process that is actually a little bit easier to so that we can use that process to solve this equation without doing all these steps of completing the square. And so it's called the quadratic formula, which we'll use to solve a quadratic equation without having to do all this long and tedious process of completing the square. So we'll see that next. But so if you feel like this process is hard, you don't have to worry too much, because the next lecture will help us do this a lot easier by using this formula. But completing the square, the idea of completing the square is useful in many algebra manipulation, so we still want to understand this process. Okay, thanks for watching.